binomial theorem. So having established that we can find the coefficient of any term, and notice that the powers of each variable increase or decrease, depending on which one it is, we can expand any binomial of any given power. Now you get given this formula in your booklets too. So it says a plus b to the power n starts with a n plus n1. Notice it starts here with n1, or I should, because you're pointing, you can see. Starts here with n1 because secretly this was n0. Yes? But we know that this term, the n0, is always going to be 1. So that's why they don't normally write it. And so we know we start, the first term starts with the same power as n and decreases by 1 each time, and the second term starts with the power 0 and increases by 1 each time. Okay? So in order to use the binomial theorem, we just need to identify which term is represented by A and which by B. So x plus y is a nice easy one to start with. I would actually suggest, we're just going to write the first 4 terms. If this was on the non-calc paper, I would probably suggest that we just identify what are the coefficients from Pascal's triangle first of all. So to do that, we would have to draw Pascal's triangle down to the 8th row. Are we happy with doing that? Yeah. Can anyone remember any of the rows that we could start off to save some time? 1, now.
4, 6, 1, 4, 1.
Okay, lovely job. Okay, so if we start with that one, that's going to make our lives a lot easier. So we've then got 1,
5, 10, 10, 5, 1. 1, 6, 15,
1,
7,
21.
35, 21. I mean,
Are you 35 again?
They're doing the adding these two numbers.
17. 1.
What?
8.
Okay.
1,
8, 28, 40, 6, 7, 56, 6, 70, 56,
28.
38,
8.
8.
Okay, hopefully you're all happy that this is the row that we want. Now, even if you can't remember which row you've been looking at, you know, or hopefully I'm telling you now, that whatever your power is going to be this second number. Okay, so that will help to decide which number you're talking about, which row you're looking for. So we've got our coefficients. We know that this is A. So our first term is going to be 1 times by A to the power 8 times by B to the power 0.
What about those dots?
Then multiplies.
Wait, why are we doing that? Are we following the formula now?
Because we're following the formula now. Now we've established our Pascal's triangle, it's taken up all our space. We're now actually answering the question. So our second term, yeah, you can ask it.
If I'm following the formula, why is it n? Why is it just n as an a? Shouldn't it be n minus 1? Like a to the power n minus 1.
No, because the first term here, look, is just a to the power n. But I've actually included the whole 1 and the b0 as well. So if I was actually following that formula, I shouldn't have done those. But I often think it helps just to really clarify what's happening. Okay, so what would the second term be? So our coefficient would be 8, because that's the second term in Pascal's. Then our A would go down to A7, and our B would now play. It would have B to the power 1. Our next coefficient would be what?
28.
28. So we're looking at Pascal's triangle, 28. A would be to the power 6, and B would be now to the power 2.
Are you not multiplying by 8? Or are you still not
I'm just not writing the dots, I apologize.
But they are.
But they are multiplied, yeah. And what's the next coefficient? 56. Then A to the power
5.
5, and B to the power
3.
3. Now, I'm showing dots because it carries on going. But they've only asked us to write the first 4 terms of it. So, just to make it a little bit neater for our first term, obviously the 1 and the B0 would just be A8, and then 8, A7, B, 28, A6, B squared, 56, A5, B cubed. Now, one other thing to note or look out for is that what's special about our powers of A and B. If this is 6 and 2, if this was 5 and 3, is there anything special about those? They add up, they will always add up to give you N. Okay? So if this was an A6, this has to be B squared, because 6 and 2 make 8, and that's what we started off with, 8 to the power 8. Okay, this is obviously a 7 and a 1, makes 8, so they always will add up to give 8. Okay? Now, it seems fine because all we had was x and y. But if we have expansions like 2k minus 3 to the 5, it becomes a bit more challenging because a is no longer just some nice number. We've got 2k as a, and b is now negative 3. Okay, so the process is going to be exactly the same, but you just have to be aware that you are going to be raising this to a power. So for example, when we start squaring things, this would be 2k all squared, which is actually 4k squared. When you've got a cubed, you're going to have 2k all cubed, which is 8k cubed, and etc, etc. If we've got e to the power 4, it's going to be negative 3 to the power 4. This could be on the non-cap paper, so you need to know how to find things to the power 4. My suggestion is that negative 3 to the power 4 is the same as negative 3 squared times negative 3 squared, because we know we can add powers. Negative 3 squared we know is positive 9, which gives us positive 81. So you want to try and look for shortcuts to help you, especially if these kinds of things come up on the non-calculator paper. You don't necessarily want to have to remember that negative 3 to the power 4 is 81. But if you remember that negative 3 to the power 4 would be negative 3 squared times negative 3 squared, then that's much easier and less daunting. Okay?